We live in a world of complexity. Yet our countryside, our cities, every man, woman and child, everything in our world and in worlds beyond has one thing in common. We consist of matter, 92 elements that pervade the cosmos. But where did matter originate? And how were those elements conceived? We wind back more than 10 billion years. This is the theory of the Big Bang. From nothing, in an instant, a tiny searing speck blasts to beyond the size of a galaxy. Space and time are born. So too, matter and antimatter. In a particle soup, matter wins by 1 part in a billion. The universe is 1 second old. It seethes at 10 billion degrees. Protons combine with neutrons to form atomic nuclei. At 3 minutes, the universe has its first elements: hydrogen, helium, lithium. During the next 300,000 years, electrons, here in blue, are tamed, captured in orbits around nuclei. They make the first atoms. And they unleash the first light, for electrons until now had blocked the passage of light-bearing photons. From an opaque universe, the fog clears. It reveals structure, clumps of denser matter building galaxies, galaxies forming clusters, clusters strung along filaments. Ever expanding, ever cooling, this is today's universe. Galaxy upon galaxy, each with billions of stars, some with planets. Expansion is the primary evidence for the Big Bang. The universe has cooled to 2.7 degrees above absolute zero, but expansion speeds on and on. There's more proof in 1964. In a galaxy like this, on a planet orbiting a star called the Sun, America's Robert Dicke has it. He reasons that radiation released when the universe went transparent should still be detectable. A year later, these men pick it up from every direction in space: cosmic microwave background radiation. Robert Wilson and Arno Penzias detect it by chance at America's Bell Telephone Laboratories. For this, they are awarded the Nobel Prize for Physics. Released originally in the short waves of ultraviolet, cosmic background radiation is stretched into longer microwaves as the universe expands. Echoes from 300,000 years after the Big Bang. The COBE spacecraft uses microwaves to map the heavens. By detecting tiny temperature variations, COBE builds this portrait of the early universe. Matter is clumping. We're looking at the seeds of galactic structure. Earlier still, from the particle soup brewed by the Big Bang, the first elements emerge. Astronomers find them today in primitive deep space gas clouds. They contain hydrogen at nearly 75%, by far the most abundant element. Helium, the second most abundant. A little deuterium, heavy hydrogen. And a trace of lithium, the first 3 elements, the first atoms, just as they would have formed from subatomic particles in that churning soup. This is an atom smasher. At near the speed of light, electrified particles are accelerated and crashed into one another. For a split second, scientists reproduce the earliest universe. The exotic subatomic particles that spawn the first elements. But if only 3 elements form in the immediate aftermath of the Big Bang, from where do the other 89 emerge? The answer is in the evolution of stars, stars like our Sun. Deep inside, at 14 million degrees, in a continuous reaction, 4 hydrogen nuclei fuse to form 1 helium nucleus. In the process, the Sun loses 4 million tons of mass every second, matter released as energy. Albert Einstein, in his brilliant equation, cracks the idea of mass converting into energy, although he doesn't apply it to stars. The British astronomer Arthur Eddington does. Eddington is convinced it's the key to how stars produce energy, but in the early 1920s, the process eludes him. The reaction, that hydrogen fusing into helium releases energy, is confirmed in 1937 by the German physicist Baron Carl Friedrich von Weizsäcker. Proof that the energy output of the Sun matches that of the fusion reaction comes from the German-born physicist Hans Bethe. It earns him the Nobel Prize for Physics. The fusion of hydrogen into helium fuels a star like our Sun for most of its life. Then there's trouble. 5 billion years from now, as the solar core runs low on hydrogen, the Sun becomes a red giant. Temperatures soar. A shell of hydrogen ignites around the core. Mercury and Venus are consumed. Earth and Mars, cinders. As the core heats, helium fuses into carbon. Then convulsions. The Sun puffs off its outer layers, 80% of its mass blown away in a nebula, a white-hot core exposed. Like this one, our local star dies as a white dwarf, compressed to the size of Earth. For his work on white dwarfs, the Indian-born physicist Subramanian Chandrasekhar gains the Nobel Prize for Physics. In animation, the death of a star that created the Helix Nebula, a star originally the size of our Sun. But Chandrasekhar shows that if the mass of its core were far bigger, the star would expire quite differently. For one thing, there'd be no white dwarf at the center of this beautiful nebula. Our Sun is a modest star. In a star 3 times as massive, and here's one to scale. It starts by fusing hydrogen into helium, just like the Sun. But unlike the Sun, when hydrogen runs out, the massive star moves smoothly into fusing helium to carbon. At a core temperature of up to 100 million degrees, this is the carbon cycle. In releasing helium nuclei, it's the main source of energy in massive stars. But what happens in the most massive stars is identified by the American William Fowler. He wins the Nobel Prize for Physics. Fowler leads a team that includes Britain's Fred Hoyle next to him and the Americans' Margaret and Geoffrey Burbidge. They show that in a star with more than 8 times the mass of the Sun, there's no collapse to a white dwarf. In this one, the core is fusing hydrogen into helium. And when hydrogen is gone, helium fuses into carbon and oxygen. Then carbon into neon and magnesium. Then neon into more oxygen and magnesium. Then oxygen into silicon and sulfur. And finally, at more than 3 billion degrees, silicon and sulfur fuse into iron. The core collapses and explodes. Supernova. Thus are heavy elements created. In 1967, Britain's Jocelyn Bell discovers a pulsar, the tiny spinning, super-dense remnant of an exploded giant. Her supervisor, Anthony Hewish, on the left, and colleague Martin Ryle, receive the Nobel Prize for Physics. So it's supermassive stars that make heavy elements, and supernovae that blast them through the cosmos. Such blast waves can trigger the formation of new stars. 5 billion years ago, our Sun and the planets begin this way. Our very Earth and the complexity it nurtures are born of supermassive stars.